Welcome back, folks. Today we are taking a look at how to do hypothesis tests for the mean. So we'll do our state plan, do conclude, and we'll take a look at an example or two. All right, so it took up a bit of space, so I put it through two different slides here. But we start by making the cross, just like we do for all the other hypothesis tests or confidence intervals. We put the big cross on our paper, and then we fill in the state section. We state what mu stands for, and it's always going to be the true mean of something. So we would write mu equals the true mean or population mean of, and then we put the context in here, always. All right, then we're going to state what alpha equals, maybe 0.05 or whatever else they give us, or 5%. If they give us other knowns like x bar or the standard deviation of the sample, we can write those down too, or the sample size, n, we can write that. All right, and we also have to write our hypotheses. So our null hypothesis will always be that the population mean, or the true mean, is equal to some mean. They'll give us that information ahead of time. All right, the alternative then has to be some not equal sign. So it could be less than, or it could be greater than, or it could be not equal to. And if it's greater than, we say it's got a tail on the left side, right tail test. And if the mean population mean is less than, we say it's a left tail because it's a tail that's towards the bottom part over here. If it's greater than, that means we think it's going to be somewhere up here. And if it's two-tailed, that means it's not equal to, so it could be below it or above it. Right, like that. All right, that's our stating. Then we go on to our planning, and when we plan, we have to first state what we're planning for. So we are doing a one sample. All right, again, ZAPTAX is in effect here. There's never a time when ZAPTAX is not. So if we're working with X bar, we are working with T. So it's a T test because we're doing a hypothesis test for the mean. You can write the word mean there, or mu, or the letter mu, either one's fine. Our conditions are very much the same as they were for the independence or confidence intervals. So the random sample needs to be stated. We need to have a normal sampling distribution. Sometimes this is also called the large sample condition. So either the population needs to be normal, or the sample size needs to be greater than or equal to 30, and then we say CLT, and then that kicks in. And if it's less than 30, we have to go back to looking at the graph. All right, so it needs to have no strong skewedness and no outliers if it's less than 30. All right, and then we check our independence condition, and it needs to be less than 10% or 0.10 of the population, and that should check out always too. All right, after that, we can do all this stuff by hand, or each separate step by hand if we want to. Like we can calculate the t value using the sample mean minus the null hypothesis mean divided by the standard error from the sample divided by the square root of n. We can do all that, get the t, and then to do the t CDF with t as either like the lower bound or the upper bound or whatever, and our degrees of freedom of n minus 1, or we can just use the t-test on the calculator. Do that one, and then just write down everything that comes out. So stats, test, and then t-test. I think it's number 2, if I remember right. 2. All right, and then we compare our p-value to alpha. We're going to do like basically the same sentence that we did with p, or when we were doing with proportions. If p is low, reject the hoe. Right? If p is not low, then we fail to reject the hoe. And then we write our two sentences. Our first sentence, sentence number 1, compares the p-value to alpha. And then we say whatever we're doing with the null hypothesis. Our second sentence is always about the alternative hypothesis, and it always includes context. All right, so here is an example. A company has developed a new AAA battery that is supposed to last longer. That's probably important, than its regular AAA battery. However, the new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours on average and are normally distributed. Ooh, that's nice. Company selects a simple random sample of 15 new batteries and uses them until they are drained. The sample mean of the batteries is 33.93 hours, and the sample standard deviation is 9.82 hours. Use alpha equals 0.05. All right, so they're asking us to do a hypothesis test here. So I'll go ahead and draw in my cross. And then we've got a state. So we're talking about means, right? Mean on average. All right, so the mean life, so M would be the true mean. Let's see, and we're talking about battery life, I guess. I guess we could say of the new batteries. New AAA batteries. All right, and let's see, what else do we know? Well, we've got our alpha is 0.05. We've got that our sample mean, x bar, is 33.93. We've got that our standard deviation is 9.82. And we've got that our sample size was 15, right there. All right, and then we need to come up with our hypotheses. So our null hypothesis is always going to be the mean is equal to something. And we're going to say that it was equal to, the original ones was 30 hours. So the alternative, we want to know, is it going to last longer? So that means it's going to be greater than 30 hours. All right, so that's everything in our state. So now we got to check our conditions for the whatever we're doing. So we have to state what we're doing. We're doing a one sample. We're working with mean, so it's a t-test for mu. So first thing we need an unbiased estimator. So we check, is there a random sample? All right, so let's somewhere it should say that we took a random, there it is, simple random sample stated. Next up, we're checking the normal conditions. Well, it was a normal population. So we had a normal population. Therefore, we have a normal sampling distribution. So we don't even have to say approximately normal. It is going to be normal. All right, so that checks out. And the last one we check our independence condition. So that means our standard deviation formula will work. N equals 15. Surely that is less than 10% of all new batteries. All right, because that is what we're measuring here. We're measuring the new batteries. All right, so as long as there's 150 or more of them in existence, we're good. All right, so now we're going to go to our calculator and we're going to do a t-test. So let me pull up my trusted calculator. Here it is. On stat, over to test, t-test. This is the second one. All right, and we're going to use the statistics. We're using stats because we gave us these numbers. So our mean is 33.93. This is the population mean. So this is the null hypothesis one. This is the 30 that we're talking about here. Wasn't paying attention. 30. There we go. Now we want the sample mean, which is the 33.93. Our standard deviation is 9.82. Our sample size is rather small. It's only 15, which might end up hurting us. And we want to know, is it going to be greater than? We want greater than right here, the null. All right, and we'll go to calculate. And we want to write this stuff down. So t is 1.55, basically, is what that'll round to, 1.55. And p, our p-value is 0.0717. And our p-value is 0.0717. 0.7 is really the important part right there. All right, so we wrote that down. Let's see, was there anything else we need to write down? Let's see, x bar, s, and we've already got those written down here, so we're good to go there. So now we're going to make our conclusion. In our conclusion, we compare this p-value to our alpha value. So we say since the p-value, which is equal to 0.07, you can add the 17 if you want, is greater than 0.05, which is our alpha, all right, so p is not low, it's greater than. So we fail to reject that the mean equals 30 hours. All right, so that means since we're failing to reject, we do not have significant evidence for the alternative. So we say that we do not have significant. We have some evidence because the mean that we got was greater, but it's not far enough based on this sample size and this standard deviation. So we do not have significant evidence that And then we're going to say what mu stands for. The true mean battery life of the new AAA batteries. And then what about it? Well, again, the alternative hypothesis is greater than 30 hours. All right. So we have one sentence about our ho, and we have one sentence about our ha, and we've got context and a conclusion, and that's everything we want right there. All right, so another quick example here. So we don't have to do the whole thing here. I just want to know, can you do the test on your calculator? A fast food manager wants to see if his store has a drive-through time under the mean time of the entire corporation, which is known to be 85 seconds. So we know that the mean for the entire corporation is 85. He takes a random sample, that condition's met, of 40, and equals 40, which is greater than 30, so like the CLT will give us the normal stuff, so that's met. I'm just doing this sloppily because it's multiple choice here. And finds that they have an average of 82 seconds. So X bar is 82 with a standard deviation of 10 seconds. What is the p-value of this hypothesis test? All right, so first we need to know, is it a one-sided test or a two-sided test? Because that will make a difference. So our null hypothesis is that the mean equals 85. Our alternative, we want to know, is his drive-through time faster? So we want to know, is the mean less than 85? All right, because we're asking about under the mean, so less than 85. All right, so we've got all the numbers we need. We haven't really checked all the conditions, but we've checked 2 out of 3 actually. So we're going to go to stat, test, t-test. We've got statistics here again. So we've got our sample size here is a little bit bigger. It's 40. All right, our sample mean is 82. Our standard deviation is 10. Still a pretty good size standard deviation. And, oops, I put the 40 in the wrong place. 85 was our null hypothesis. 2 for 2 here, huh? And then there's our sample size of 40. I was just going the numbers in order here. All right, and our alternative is that our mean value is going to be less than what it was. And we check, what do we get here? Our p-value, there it is, 0.0326. Oh, that's it right there. There's our p. All right. So that means we would, since that is low, I mean, we would usually compare that to 0.05, we would end up rejecting, but it didn't ask here what we would compare it to. So we're not actually drawing a conclusion, we're just finding the p-value. All right, so that's how we do a full test and find the p-value. We'll do another one with data and probably another one without data and the next one. So just more practice coming up.